Hello everyone. Welcome to our Hello everyone. Welcome to our fourth tutorial in thermodynamics. Today's tutorial is going to be based on entropy. What is entropy? Entropy is a degree of measure of disorder or the measure of or degree of randomness or measure of randomness or disorder within the system is known as entropy. Okay, so summary. We started with entropy. Okay, before starting with entropy, you have gone through something called Clausius inequality. What was from Clausius inequality? You came up with two important things. One was when the cyclic integral of del q by t is equal to 0, then your process is a reversible process. When the cyclic integral of del q by t is less than 0, then your process is irreversible process. Okay, so what was the from Clausius inequality the conclusion? Always the cyclic integral of del q by t is less than or equal to 0. Okay, and then you also learned that for an internally reversible and isothermal process, okay, we know delta S is equal to q by t0. Okay, it can be so this relation which we said right now, the delta S is equal to q by t is valid only for internally reversible process. Okay, from this relation what you can say? You can say that delta S decreases as q decreases, which is when q is going out of the system, delta S decreases, and delta S increases as heat comes into the system or as q increases or q going into the system. Okay, that was about entropy. Then you learned about increase of entropy principle. Okay, where you had a process going from 1 to 2, which was a process we had, let's say for example 1 to 2, a process going where it was reversible or irreversible, and from 2 to 1 it was internally reversible. Okay, and from this increase of entropy principle, you came to know that S generation, a new term called S generation. Okay, S generation is equal to 0 if your process is reversible, and S generation is greater than 0 if your process is irreversible. Okay, so if your process is reversible, S generation is equal to 0. S generation equal to 0, and S generation greater than 0 if your process is irreversible. Okay, and one more thing you came to learn from the S generation less than 0, this process is impossible to happen. It will never happen, or it's impossible to happen. Okay, so over there you had three remarks which you have already learned. One was what? Process can occur only in certain directions, which is in the direction of S generation is greater than or equal to 0. Then there is no conservation of entropy principle, or conservation of entropy principle doesn't exist, or there is no something like that. And what was the third thing? As irreversibilities increases, entropy generation also increases. As irreversibilities are increasing, what is also increasing? Entropy generation is also increasing. So in short, what is entropy generation? Entropy generation is delta S of the system plus delta S of the surrounding. So what did I say? S generation less than 0 means there is nothing called, or there is nothing such a thing which is called negative entropy generation. That doesn't exist. So S generation less than 0 means it's an impossible system. The system is not going to happen. Okay, then you have gone through entropy changes of a pure substance. Then you went to something called isentropic process. What is isentropic process? Isentropic process is a process that occurs only if your system is internally reversible, first of all. Second of all, it should be adiabatic process. Adiabatic means what? There is no heat transfer happening, means it's insulated or heat is not transferring between the system boundaries. It's fixed, as well as the system should be internally reversible. So only that means there is no irreversibilities. Only at this time you have something called as entropic process, which is entropy is going to be constant. Then you have gone through the property diagram of TS diagram and HS diagram, which is also known as molecular diagram. Then you learn what is entropy. Then you have gone through the two TDS relations. The first TDS relation for a closed system, second TDS relation for an open system. Then you went through entropy change of liquids and solids, which is also known as incompressible substance, and you have gone through entropy change of ideal gas. So right now let's begin the entropy change of pure substance. What do we have over here? We have an isentropic. Isentropic means what? The entropy is constant throughout the system. Isentropic steam turbine. Okay, processes 2 kilogram per second of a steam at 3 megapascal, which is exhausted at 550 kilopascal and 100 degrees Celsius. 5% of this flow is diverted for a feed water heating at 500 kilopascal. Okay, so isentropic means what? Like we told before, isentropic means this is it is internally reversible, and this is the process is adiabatic as well. Only then we will have isentropic. Means entropy at 1 is equal to entropy at 2 and 3. Okay, so that is called isentropic. So what is the question about? The question is about determine the power produced by this turbine. So let's write what is given. So mass flow rate m dot 1 is given to be 2 kilogram per second. What is also given? P1 is given to be 3 megapascal. What is also given? P2 equal to I'm considering this has one inlet, this has one inlet, and the system has one inlet and 2 exits. Okay, so this is state 1, this state 2, I took it as 500 kilopascal is given, and P3 and T3 are also given to us. Okay, what is P3? P3 is 50 kilopascal, and what is T3? T3 is given to be how much it is? 100 degrees Celsius. Okay, so based on this we are going to perform analysis. Okay, so let's start with performing our analysis. So what is the first analysis we are going to perform? We are going to perform the energy balance equation, which is energy in, the amount of energy coming in, energy in minus energy out is going to be change in energy of the system. Okay, the energy can come in 3 forms. Okay, it can come in as mass, heat and work. It can come in as mass, heat and work. Okay, so in our case energy is coming in only in form of mass. Okay, but before that the delta E of the system by delta T or delta I wrote it d2 or dt, this part is equal to 0. Why? Because we are having a steady flow device, which is a turbine, so it's a steady flow process. Okay, steady flow, so that's why there is no change. Delta E of the system by delta T is equal to 0. So from here, like I told you, mass energy, the rate of net energy transfer can be by heat, mass or work, but in our case energy is coming in form of mass. So mass m dot 1 h1 minus what energy is going out from 2 H2, which is mass is going out from 2, minus mass is flowing from 3 as exhaust. And what is also having, we also have the since we are dealing with turbine, so we have work out. So instead of turbine, if it was a compressor, we will have working. So compressor takes the work, turbine gives the work. This is equal to 0. Okay, so you can write as W out is equal to m dot 1 H1 minus m dot 2 H2 minus m dot 3 H3. Okay, now let's perform our conservation of mass or mass balance equation. We know mass in minus mass out is equal to change in mass of the system, dm by dt. Okay, but since we are dealing with a steady flow system, this is going to be 0, so we can write it as mass in equal to mass out. Okay, which states that m dot 1 is equal to m dot 2 plus m dot 3. Okay, we know that m dot 2 is what? It's 5% of m dot 1. So m dot 2 is 0.05 of m dot 1. We know that. Similarly, what is also known? It's also known m dot 3 is, if 5% is gone here, what is remaining? We have 95%. So 95% of m dot 1. So this is going to give you 1.9 kilogram per second, and this is going to give you 0.1 kilogram per second. Okay, so now you have m dot 1, you have m dot 2, you have m dot 3. Now what are the unknowns? You have H1, H2 and H3 are unknown, so we need to find that. Okay, so let's start. What is given? We know P3 is equal to 50 kPa and T3 is equal to 100 degrees Celsius. Okay, so from here itself it is very clear that it's a superheated vapor. So H3 and S3 from table A6 I need to find. So I have found the values to be 2682.4 kilojoule per kilogram. Okay, similarly S3 is equal to 7.6953 kilojoule per kilogram Kelvin. Okay, these are from where? These are from table A6. Now for state 2, what we know? We know P2 is equal to 500 kPa, and we know S2 is equal to, S3 is equal to 7.695 kilojoule per kilogram Kelvin. So from this to, again it's a superheated, so we can find H2 is equal to 320.5 kilojoule kilogram. Okay, this is also from A6. Okay, and now I have what P1 is equal to 3 megapascal and S1 equal to S2, S3. Since isentropic, I got H1 is equal to 3851.2 kilojoule per kilogram, which is also from table basis. But here I have done some sort of interpolations as well. Okay, so when you are doing it, I hope you know how to do interpolation as well as taking values from the table, since you have done it a couple of times. Okay, so now we have H3, we have H2, we have H1. Now it is easy to find, right? Because what was W out? W out, okay, the rate of power output is equal to mass flow rate 1 H1 minus mass flow rate 2 H2 minus mass flow rate 3 H3. So if you plug in the values, you will get the output has 2285 kilowatt. Okay, so you can see that plugging the values as well as finding the properties are very easy. It's just a matter of math calculations, plus you just have to go through the thermodynamics table and find the properties. But most important thing is understanding the problem. Okay, so like we see in the beginning, we applied the energy balance equation. We found what is the energy coming in, what is the energy going out, and then since we are dealing with a steady flow device, we cancel the dE by dt, we cancel. So these are the things you need to perform. Okay, and we also said we are performing for an entropy change of a pure substance. So like I told you, these are the things you just need to remember, or you need to figure out from the question. The most important thing was this is an isentropic process. That's why we found that S3 is equal to S2 is equal to S1. See, S3 equal to S2 equal to S1. Okay, this happened only because it's an isentropic process. Okay, so now I have taken an example from entropy changes of ideal gases. Okay, so here what do you have? You have a 1.5 meter cube insulated rigid tank. So rigid tank means what? Volume is constant. Okay, contains 2.7 kilograms mass of carbon dioxide at 100 kilopascal. So since I wrote that heading, you all know it's an ideal gas. But from the question, how you will know it's an ideal gas? Carbon dioxide. It's a gas. It's an ideal gas. Okay. So now the paddle wheel work is done on the system until the pressure in the tank rises to 150 kilopascal. So you have the mass, which is 2.7 kilogram of carbon dioxide is there in this tank. Okay, at state 1 or initially the pressure is 100 kPa or kilopascal. Now the pressure is raised from P1 to P2, which is from 100 to 150 degrees Celsius. 150 kilopascal, sorry, 150 kilopascal. So from 100 kilopascal, the pressure is increased to 150 kilopascal. What is the question asking you to find? It's asking you to find entropy change of carbon dioxide during the process. What is also given? It's a constant specific heat. Assume it has a constant specific heat. So Cv is constant. That means it's not depending on the temperature. It's a constant value. Okay, so Cv is equal to 0.657 kilojoule per kilogram Kelvin. This is from table A6, okay? From table A2. From table A2 we have found the charge. Not A6, it's from table A2. For carbon dioxide I have found the constant. Why did I take CV? Because we are dealing with a closed system. The system is insulated. So the gas is not from crossing its boundaries. It's an insulated closed system. Okay, as well as heat also. Okay, now let's perform our analysis. What do we have over here? I said we have an ideal gas. So we know, let's plug in the ideal gas relation PV equal to R. So we have P1 V1 equal to R T1. Similarly, we have P2 V2 equal to R T2. From this I can get right as P1 V1 by T1 equal to P2 V2 by T2. But we know that V1 is equal to V2. Why? Because we are having a rigid tank. So volume is fixed. It's given rigid tank. Okay. See, these are how you need to understand the question. So now what happened? The volume is fixed. So these are getting cancelled. So what do we have? P2 by P1. Okay. Can write as T2 by T1 equal to P2 by V1. If I plug in the values, it is 150 over 100. Any value without a unit is useless, so we need to plug in the units. Kilopascal equal to 1 point. So the ratio of temperatures T2 by T1 is 1.5. Okay. So now, like we said, in the ideal gas, we also had two important things. One is constant specific heat, one is variable specific heat. But here we are dealing with constant specific heat. Okay. So now let me use the or plug in the TDS relation for a closed system. What was the TDS relation for a closed system? TDS is equal to du plus P dV. This was for a closed system. Okay, or you can write it as ds is equal to du by T plus P dV by T. We know that P is what? P is equal to, we can substitute the values or substitute P is equal to R T by specific volume, and we also know that du is equal to CV PT. So now I am going to substitute this into these two into this equation. So I can write it as ds is equal to CV dt by T plus R T by T dV by V. T and T is getting cancelled. Now I am going to perform the integration. But one more thing you have to do, you have to keep in mind is over here your specific heat is constant, so it will be out of the integral. So if I perform the integration, I'll get delta S is equal to CV integral going from 1 to 2 dt by T plus R is outside constant 1 to 2 going from state 1 to state 2 dV by V. Okay. Now I need to remind you one more thing. You have learned two analysis. One is approximate analysis, one is exact analysis. But over here I am going to do the approximate analysis. So I get delta S after the integration to be CV average. Okay, len T2 by T1. I performed the integration as well as substituted the limits, plus R len V2 by V1. Okay, but we know that this part is 0. Why? Because V2 equal to V1, right? And len of 1 equal to 0. So this part is 0. So what do we have? Delta S is equal to CV average len T2 by T1. T2 by T1 we know it is 1.5. So delta S, capital S, entropy change is equal to M CV average len, we said T2 by T1 is 1.5. So I'll just substitute other values. So if I plug in the value of mass is what? 2.7 kilogram okay, multiplied by what was CV, we found it on 0.657 kilojoule per kilogram Kelvin, and len of 1.5. We get it as 0.719 kilojoule per Kelvin. Okay, so you see, like I told you, the performing the analysis are very easy, or doing the calculations are very easy. The most important thing is how you assume your problem and understanding what are given in the problem and performing the analysis accordingly. Okay, calculation and plugging in the values are just a matter of math. Okay, so thank you very much. If you have any questions or any concerns regarding this tutorial, we can discuss it in the live session. Have a nice day. See you in the live session.